Hi, my name is Paul Boven, and I'll talk about VLBI with GNU Rabbit. VLBI with, good start. VLBI with GNU Radio and White Rabbit. Well, GNU Radio you all know. White Rabbit you have maybe heard a little bit about. I work at the Joint Institute for VLBI in Europe called JIVE, and in my spare time I also do a lot of radio astronomy on this old dish here, the 25-meter Dwingeloo dish that you might have heard of before. So a little bit of an introduction. Why are we doing this VLBI stuff? If you take like the Hubble Space Telescope, say at 600 nanometer wavelength and a size of 2.4 meters diameter, that you can easily, it's just a ratio, calculate that the resolution that you can get out of it is like 0.06 arc second, where you have 360 degrees, gets divided in minutes, gets divided in arc seconds, and this is a fraction of an arc second. Now if you take a 25-meter telescope, so that's 10 times bigger, but you have a wavelength in the order of 6 centimeter, your resolution is suddenly 10,000 times worse. Actually, with this kind of resolution, you would have like 4 or 5 pixels on the full moon. So to get an equivalent resolution, to see the things in the radio spectrum that you also want to see in the optical, or that you can already see in the optical, you would actually need a dish of 250 kilometers. Yeah, right, which we can't have, apparently. So the solution to this has been found is called Very Long Baseline Interferometry. So that's what the VLBI stands for. It is connecting radio telescopes all over the world and using them in phase as a giant, I would almost say, MIMO array. This chart shows the European VLBI network. It's not like the United States, for instance, doesn't have any radio telescopes. They have a great VLBI network of their own, but I work for JIVE and we do the Joint Institute for VLBI in Europe. And we run the European VLBI network. So what can you do with VLBI? You can get unprecedented resolution. The image to the left has already been shown. That is the black hole in M87. And the resolution there is really sub-micro arc second. The image to the right is actually a very interesting image. You have like a radio source that's 11.7 billion light years away. And then between the radio source and us is a cluster of galaxies that's much closer. And the radio signal is actually being bent around this cluster by gravity. And that gives rise to this ring-shaped structure called an Einstein ring. And the people who made this image were actually able to deduce the mass distribution in the galaxies and also details about the very far away source that you could not possibly see itself. So if VLBI does not yet give you enough resolution, you can get more magnification if it happens to line up with some very heavy galaxy cluster, for instance. So what do you need? You need VLBI in a nutshell. A virtual radio telescope where the diameter is comparable to the largest distance between the dishes. The resolution you get is on the order of a milli-arc second, or even better sometimes. So all these telescopes look at the same source at the same time. Before you actually process the data correlated together, because the Earth is rotating, and if you were at the equator, you'd actually be rotating at 456 meters per second. So all the Doppler shift and all the delays to all the different telescopes from the direction that you're viewing in, they need to be taken out. Then you calculate the complex cross-correlation on each of the baselines, so from each telescope to each of the other ones. And you fill this in a so-called UV plane where you have basically the wavelength as the two axes, and then if you do a Fourier transform of this, you actually get an image. Except it's a very poor image because most of this UV plane is empty because you didn't have a telescope at that particular distance. So you have to guess what the data would have been like. And for that reason, there are very, very complicated algorithms to then make a very clean and nice image. So what you need is, first of all, a radio telescope, and not just one, you need multiple, because otherwise you can't do interferometry. As many as you can, as big as you can, of course. Each of those needs a very stable frequency source, because you want all those phases at observing frequencies of, say, 10 gigahertz. You want the phases to be stable to each other within 1,000 seconds. And you can't really do that over a piece of coax that you run from here to Germany. You need a lot of bandwidth, because the more bandwidth we have, the more sensitivity we have. Bandwidth actually sensitivity scales as the square root of the bandwidth. You need a supercomputer to do all the processing that comes with this. And then you need a lot of detailed work, like you need very accurate telescope locations which actually take into account the fact that not only does the sea go up and down with the tides, but actually the Earth deforms by up to 40 centimeters. You don't notice because everything around you does the same, but it goes up quite a bit and down again. All these details do you need to take care of. So for the rest of the talk, I'm sort of going down this list of things you need and see what I can find. So we start with a radio telescope. So in my spare time, I'm a volunteer at the Dwingeloo Radio telescope. It's a very ancient instrument. At one time, it was the largest fully steerable radio telescope in the world. It's a 25-meter diameter dish. And it nowadays is being run by volunteers of the CAMRAS Foundation. And I'm one of those. We do, first of all, maintenance, try and keep the instrument in order. We do radio astronomy, we do ham radio, things like moon bounce, we do education and outreach, we do SETI, we do satellites. You certainly might have heard of some of our satellite observations that we've recently done, and then art projects and many other activities. On the left, you see the official opening in 1956 by Queen Juliana of the Netherlands. And I couldn't resist this. This is yesterday. This is actually our queen and our king. And in between those two, two of our volunteers, they visited yesterday. And what you see on the right hand is what we showed them, is a GNU Radio plot of, in real time, of the galactic hydrogen line at 21 centimeters. Yeah. Well, I see there's more royalists here. Okay, so a little bit more about the technical details, because that's what we're here for. For wideband observing like VLBI, like I said, sensitivity scales with the square root out of the bandwidth. And now, you always run into financial limits. The amount of disk space you have, the amount of network throughput you have to get somewhere, and then to get the best sensitivity out of it, you want to use fewer bits. If you can represent your data with fewer bits, you can actually put more bandwidth into your link. But your quantization noise gets worse. So that is a trade-off, and for VLBI, actually, we almost always use 2-bit quantization, only 2-bit. I know Great Scott yesterday said they do it with 1 bit, we do 2-bit quantization only. Now, 2-bit quantization should not be difficult. It's simply you left shift your values until you have 2 bits. Turns out that actually it is a little bit difficult. There's 2 kinds of quantization. There's the C-style truncation, where everything between -1 and +1 actually gets rounded to 0. But in signal processing, we want more like anything between -0.5 and +0.5 to round down to 0, because otherwise you get like a huge discontinuity in your rounding function. The nice thing is that GNU Radio would do both. What you see here is a graph of all the values that round to 0. And nicely, as expected, values between -0.5 and +0.5, they round to 0, except every 8,192 samples. Occasionally, you get a much larger range that rounds to 0. And the reason for this is that most of the code is optimized through the Volk library, and that uses SSE in this case, and does the right thing. But then there's a little few leftover samples that actually get processed in C, in the same block, and that does C-style sampling, C-style rounding, and you get this effect. And apparently nobody had looked at this in detail before, so this is the first time I kind of got involved as a contributor to the GNU Radio project, saying, that's not right. Fortunately, it's been fixed now. Another challenge was high bit recording, and I'm telling you here how we did it, but maybe there are people here who have better solutions, and I would love to hear it. We had a X310 with two TwinRX modules, and at worst you can get, or maybe I should say at best, you can get 12.8 gigabit per second out of that. And of course, if you have an expensive SDR like this with expensive models, etc., you want to actually capture that data, and that's not trivial. I could easily record to memory on my machines, but you run out of memory very quickly. I had this server that has like 36 disk slots. I had 18 disks that I made a RAID 0 out of it, and even with UHD, you can't really do any sensible bandwidth, you just start losing packets. And because we are very sensitive to the phase of the whole thing, as soon as we lose packets, we're gone. So then I found SpecRec, spectrum recorder, which is part of the GR analysis. And that does something a little bit more sensible, where you have like a large ring buffer of memory that the thing records in, and at the same time writes to disk. It doesn't wait for it all to be filled and then write to disk, because then it's so busy writing to disk that it can't take the next samples. And with that, at least at 50 megasamples per second on just one port, it would keep up for hours sometimes, often not. Anyway, if there are people have better ways of recording this, let me know. The timestamp is also really important. If you're cross-correlating this data, you need to have a time reference on all your data, so you are actually cross-correlating data from the same point in time. And GNU Radio has some facilities for it. Many USRPs, they have like a GPS clock. You can start your flow graph and sync it to GPS. But GPS is not nearly good enough in the timing for what we need, and especially not in the frequency reference, in the phase stability. So one of the things I did, and this is actually documented in the Ethos knowledge base how you should do this. It is just unfortunate that every time I write a flow graph, I need to add this in by hand. So you wait for the PPS edge, then you look at your PC, what time is it now? Or actually, you wait for the PPS, you wait a little bit so that you're sure you're in the middle of the next second. And then you read out your PC time, which is presumably locked to NTP, and then you set that time. You tell your USP at the next rising edge of the PPS, that is going to be your time, and that actually works. It just takes more than a second to do the synchronization, but that's not an issue. So one of the things I hope to contribute is to actually make this part of UHD again. So now we get to the actual GNU Radio part. The data that we process in VLBI is usually done in subbands, and the standards that we use say you use 16 megahertz subbands. So I have a Twinner-X, which is sampled at 100 megasamples per second. So the recorded data comes in here as shorts, which are turned into floats. And then the first thing I do is resample it from 100 megasample per second to only 80, because there's only 80 megahertz of spectrum in it anyway. So that's that block. And then I go to a polyphase filter bank, so I create 5 channels. And this multiplier and this source, they actually shift the channels with like half a channel. The idea is that the band edges, which I can't use, end up in the same polyphase channel, and they go into this null sync. We throw them away. All the other channels, we do the same thing 4 times, which is we double the sample rate, we shift the spectrum up, and then we throw away the imaginary part, which is actually the same thing as going from complex to real values. We've gone from complex to single sideband, upper sideband. And then we read them out in order, in a particular block size, and then over here there are floats, over here we go to 8-bit representation. This should have only been 1 block, but due to the bug I mentioned earlier, I'm actually doing it in 2 steps. Over here I bring it down to 8 bits, and then here I have a lookup table to go from 8 bits to 2 bits. This is a homegrown block, a new GR block that actually puts the timestamps on it and the name of the designation of the telescope and which frequencies, etc. And that makes it standard VLBI data format. So that's why it's called a VDIV block. And finally, we write it to file, and then we can put it into the correlator, and the correlator will compare it to all the channels from all the other telescopes and get our image. Now, using this flowchart, and we're now last year, August, we actually did our first VLBI observation with the radio telescope, except it wasn't the first. This telescope did it in 1978. They borrowed a rubidium clock somewhere. And we did the same thing. We borrowed a rubidium clock, and we cross-correlated between the Westerbork telescope in the Netherlands, our Dwingeloo telescope, and the Joddelbank Mark II radio telescope in the UK. And what you see here is time slots and the cross-correlation in each of these time slots, and you see that there's only 1 peak, which is nicely in the center, which shows that this actually works. Except at that time, we could only record to memory. We could only record 10 seconds at a time, but that was good enough to show that this works. So this is half hobby, half work, and for work we got involved in a project called ASTERICS, which is a European Commission Horizon 2020 project. And its aim was to address all kinds of interdisciplinary issues in astronomy, astroparticle physics, particle physics, etc. And one of the fields that all of these institutes, all these observatories and experiments suffer with is accurate timing. And White Rabbit is a very interesting way to do it. There were lots of White Rabbit work packages in this research. And we were going to work with this as well. And we were going to show that White Rabbit as a time and frequency reference distribution is good enough as a time source for VLBI, so almost as good as a hydrogen maser clock. So not everyone here is familiar with White Rabbit. On the left you have a White Rabbit switch. Then you have like optics. And this is not your normal fiber optic stuff. This is only one optical port because you're using the same fiber back and forth in the back and forth on the same fiber. You do it at different wavelengths though. And that's why it has only one fiber connected instead of the normal pair connection you would have. So you go through a fiber, and at the other end you have another block, another optical converter, and you have your end point, and that gives you out your pulse per second and your 10 megahertz again, and it completely compensates for the unknown and changing delay through the fiber. And it does this by measuring the round trip time up to picosecond accuracy. So in our work package, we put some interesting challenges. So here you have the Westerbork telescope that I already showed, their hydrogen maser. This is a White Rabbit switch, and from there we could go 67 kilometers to the north to the city of Groningen, where we did optical amplification and went back to the same place we came from. And then more optical amplification, and then we would go over 35 kilometers of dark fiber to our radio telescope in Dwingeloo. Now the interesting thing here is that we were able to do this over an existing public dense wavelength division multiplexing network. So we didn't have to run our own fibers. We didn't have to interrupt the existing users of this network, but the tricks we used allowed us to insert these wavelengths outside of the existing wavelengths, to add our own amplifiers, because White Rabbit only works on a single fiber, so your amplifiers actually need to be bidirectional, which is very unusual in telecommunication industry, and actually raised a few eyebrows when we first discussed it with them. But fortunately, the Dutch research and education network provider, SurfNet, was very willing and interested in helping with this, and we managed to set up this link. And for the people who are actually into synchronization, this is the LM deviation that we got, where the red line and the green line, red and the blue line continue into one each other, give us the actual achieved stability of the clock. And in black, we have the performance that a hydrogen maser would have according to the sales brochure. So as you can see, everywhere we're like within an order of magnitude of the same stability, and at over 1,000 seconds, eventually we cross over and even become better. Unfortunately, that's a range where for VLBI it's not that interesting anymore. But we were like within an order of magnitude of what you can do with a hydrogen maser. The problem we had is that the radio telescope in Dwingeloo is still like 300 meters away from the building. So then we had to put in some fiber. And like I said, this is half hobby, half work. This was definitely hobby part. So somebody was kind enough to give us 500 meters of fiber. The only problem is it is 144 strands, so it's a little bit more than we needed. And we had to go from here, around the building, there, and then through the building. So we rented a digger, dug some fiber or some tubing, then we inserted the fiber and built a system so that fiber can actually rotate around the axis of the telescope so it doesn't get kinked as we turn the whole building, which turns with the dish. Then we also ended up splicing our own fiber, which is, each fiber here is like 1/8 of a millimeter in size. It's really nerve-wracking work to do. And what we ended up with in the end, inside the Faraday cage, inside the radio telescope, is this setup. So you might recognize some of these blocks. This is an X310, and I managed to find an X300 somewhere else, so we have 2 of them. This is the incoming fiber, and So we had this long 169 kilometer link, and we also had the direct 35 kilometer link, so we could actually compare the performance. And this is the White Rabbit switch that takes care of the timing. And this is the second White Rabbit switch, so we could run one on the long link and the other on the short link and run them at the same time. Actually, these are not, I should also mention that these are not the standard White Rabbit switches. You don't get this kind of performance on the standard White Rabbit switch. We used an extension to the White Rabbit switch, which is called the low jitter daughter board. And on one of the switches, we also had a special cleanup oscillator. And that allowed us to actually get to the performance that we were achieving. So now it's time to show that all of this actually worked. And unfortunately, the project was getting very much at its end. It ended in April this year, and by now we are in March, so it's getting a bit tight. But in March, we had an overall network monitoring experiment with like 20 dishes officially participating, and we unofficially participated with our hobby dish as well. Problem is, all these observations, VLBI observations at 21 centimeters are at 18 centimeter wavelength, 1650 megahertz, which is slightly higher than the hydrogen line, and the Dwingeloo dish didn't have any receivers for that. So we had to install new low noise amplifiers, which means you have to get into the elevator. The elevator goes up, and then you go to the receiver, and then you can pull out the receiver and bring it down with you. It's a lovely picture, except we had wind force 6 and rain. Yeah. Still, we managed to do this, and we managed to get our first fringes on a remote maser. And what you see here is, again, the amount of cross-correlation for different time offsets, and you see one very nice peak. And this is actually between the Dwingeloo dish and the 100-meter diameter Effelsberg dish. Also, because we last minute bought different preamplifiers, we didn't quite have the sensitivity that we thought we had, but later on I did more observations, and what you see here in black is the actual performance of the link back-to-back without doing VLBI, and then this again is an Allen deviation, so over here you see the amount of frequency noise, and what you see over here is your averaging time. And what you see here is that for the 35 kilometer and for the 169 kilometer, basically the performance is exactly the same, but then eventually it starts to diverge, and that is because these measurements were not done at the same time yet, and you start to see the effects of the ionosphere. Still, we can see that the performance is pretty close to the link performance. We're not losing much, and this is actually an observation that ran for 1.5 hours each. The flowchart I showed earlier unfortunately runs even on a brand new i9 19900K or something at 1/5 of real time. And that flowchart is actually only a quarter of what I want to do, because the TwinRX actually has 4 inputs. So, having been to previous GNU Radio events, I said, I'm going to do this in RF NOC. Shouldn't be all that hard. I mean, I've got 100 megahertz of data, 100 megasample coming in. I want to break this down into 4 channels, and I want to quantize it at only 2 bits. Because originally I'm getting like 3.2 gigabit per TwinRX input, but what I actually need is, once it's quantized at 2 bits, it's only 256 megabits. So, and also the X310 has like a huge FBA in it. So this is the progress so far. This is like the block that's already in there that gives you your samples out of your axis stream. And then I wrote a fractional resampler, 5 to 4, to go from 100 megasample to 80. And then I made 4 DDCs that have a 5 to 1 resampler after them, so that I would have 4 streams of 16 megasamples each. Then I wanted to 2-bit quantize them and interleave them, get the timestamps on it. But actually at this point, my FPGAs are already getting pretty full, and I'm not nearly at a quarter of what I actually want to put in there. So if there's people here who are more knowledgeable about RF NOC, I would definitely like to hear from you. Should this even fit? Is this like way too big anyway, and should I find a different solution? So far we're doing it the slow way, but I would really like to do this in real time. And that sort of brings me to the conclusions from this story. We have a working VLBI backend using a commercial off-the-shelf SDR, and it works. And we can process the data in GNU Radio to get it to the same format that any radio telescope that does VLBI. And we're doing reference clock transfer using White Rabbit, and not just over 10 kilometers, but we can do 170 kilometers with a frequency stability that we've calculated is good enough for observations at frequencies up to 14 gigahertz. And we get timing accuracy better than 1 nanosecond. So yeah, all of that works pretty well, and that is where I break for questions. Thank you.
So, you mentioned that the White Rabbit switch that you're using isn't, or you made a comment that it's somehow different, or that you wouldn't be able to get the precision you needed with an actual White Rabbit switch. Can you elaborate on that a little bit? What is the performance of White Rabbit naturally lack that you had to make up for?
So it was improved in 2 ways. The low jitter daughter board really makes the Allen deviation, like, I think more than a factor 10 better. And then there was also a cleanup oscillator that takes care of lots of nasty noise spikes that you have in there, RFI spikes. And the combination makes for a really clean signal. And I have, from a longer presentation that I can show you, we have pictures, and it's also been published how we've done that. Yeah.
We have time for one. Oh, there we are.
Marcus.
So assuming I know a field near Karlsruhe where like 10 3-meter dishes stand around, how would I go about getting, maybe a reliable clocking signal without running a fiber optic cables? Can I like build something that's based on a radio receiver to discipline a local oscillator?
I have to say, I hardly could hear you.
Oh, sorry, then, yeah. If I have a dish somewhere a couple kilometers away from my clock source, how would I go about disciplining a local oscillator without running the fiber? Can I do that with like a radio receiver, maybe?
Not really something I've looked into. I would say run fiber. It's lots of fun, but...
Okay, there were no more hands, I think. So maybe we can have one more round of applause.